Building off our discussion of probabilities and moments, I now want to take this time to discuss what's known as the Maxwell-Boltzmann distribution. And so this is a fairly famous sort of concept in statistical mechanics, because basically what it deals with is the distribution of particle momentums within a system. Okay? And the reason that this is important is that the distribution of particle momentums, at least the way that we calculate it, it's going to be general. It's a thing that's general to a lot of systems, and also it's analytically tractable. Or in other words, we could calculate it and develop analytical solutions for calculating it. So that's why there's, at least in introductory statistical mechanics courses, there's a lot of emphasis on studying it, calculating it, and understanding it, because you can just derive a simple expression to calculate. Okay? All right, and so in order to derive the Maxwell-Boltzmann distribution, what we're going to start out with is a goal in which we just want to calculate the probability of our system in calculating, or the probability of our system as a function of the momentum for the first particle in the x direction. Okay? And so, to start that, we're going to start with just the definition of the probability of our system for all momentums. Okay? And we know from the previous discussion that we could write the probability in terms of the momentum like this, where we have our kinetic energy Hamiltonian divided by the integral. Okay? All right, and so just as a reminder, the kinetic energy portion of the Hamiltonian is described like this: the summation of momentum in the x direction plus the y direction squared plus the z direction squared. Okay? And previously, when we discussed the continuous form, continuous partition function for the canonical ensemble, we showed that this integral here is just equal to 2 pi m kBt raised to the 3/2 n. Okay? All right, and so with those previous results in mind, we could simplify the probability like this: 2 pi m kBt to the 3/2 n exponential negative k over kBt. Okay? To further simplify this expression, I'm going to multiply it by Planck's constant raised to the 3n over Planck's constant raised to the 3n, right? Such that I'm only multiplying this by the number 1, so it's not actually changing the value. But by doing this, I can combine these two things together to form the thermal wavelength lambda raised to the 3n. Okay? So our probability expression now further simplifies down to this: lambda raised to the 3n over h to the 3n times the exponential negative k p to the n over kBt. Okay? And so now we have an expression for the probability as a function of the momentum in every direction for every particle. But in the end, we just want to describe the probability in terms of the momentum for the first particle in the x direction. And so to simplify this down even further, what we're going to do is we're going to integrate our probability in terms of all the momentums. We're going to integrate it with respect to every dimension or to every degree of freedom except P1x. Okay? So that way the P1x dependence still stays around. And so to get the probability as a function of P1x, we'll just integrate Ppn starting with dp1y, dp1z, dot dot dot, all the way to dpn. The entire set, except we don't have P1x here. Okay? Alright, so if we go through that integral, (3n over h(3n). We go through that integral, what we're integrating is this. Over 2 pi, or 2m kbt, no pi there, summation pi x squared plus pi y squared plus pi z squared dp1y dp1z dot 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 to whatever the final sort of variable is. Okay? And so essentially, we work this out even further, what we're going to get is, because we're not integrating this with respect to pix, we could take advantage of our exponential rules and pull that term out. 2m kbt, and then everything else we're going to integrate. So I'll write it like this. M kbt dp, that's going to be the 3n minus 1. Okay, since this represents the degrees of freedom we're dealing with. Okay. All right, and so if we work this out even more, you have p1x equal to lambda 3n h3n exponential p1x squared over 2m kbt. Right, and that integral will give us h3n minus 1 over lambda 3n minus 1. Okay? Right, we've seen this, we've already done this integral before, and that's what the result it'll give us. Of course, we could cancel these out, and what we get is lambda over h exponential pix squared over 2m kbt. And then if we go to the next page, I'll write this probability expanded out. So now it's going to be 2m kbt raised to the 1/2 times the exponential negative p1 x squared over 2m kbt. Okay? And so this expression here is the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. Right? And so here we're describing the particle probability as a function of its momentum.